Our final speaker today is Joao Vieira, and he will speak to us about two-step panel data mode regression with interactive fixed effects. So, Joao, the floor is yours.
Thank you everybody for coming to this presentation. I just have to say that I don't work on this for like 2 years, so it's just an old work that I did. So basically, we can start with the most simple case that looking at the measures of central location, we can see that both of them, or the three of them, like the median, the mode, and the mean, they both collapse on the same value when the distribution is not skewed. The problem is if you have some positively skewed or negatively skewed distributions. For example, if you have some outliers or some data that, for example, it's better introduced in a data set, for example, for a typing error or something like that. This case needed to be a very consistent typing error. We have a problem because, or we remove those data values, then we have a problem, for example, with what could be the cutting value, or we keep them in the data set. And then, if, for example, you would be using the linear regression, that could bias our results, for example, or push our beta parameters in the direction of those outliers. So, before going ahead of myself, for each of central measure tendency, we have, for example, the conditional mean, you have the mean regression or the with squares. For the quantiles, you have the quantile regression. And for the mode, well, now you have the mode regression. It's the one I'm going to talk about. On our setting, we consider or we just assume that we have a unique mode. So, for example, here, if we have another bump, here we are not considering these cases. There are some papers that do it. They do it in non-parametric way. And we also assume a linear form on our regression. There are also other papers that does not assume this. The literature on this has exploded in the previous years, by the way. And so our problem is mainly because asymmetry on heavy tails on the regressions, mainly on the linear case. And some critics usually tell me, like, why not using the quantile regression? Some people try to do it. The problem is if you want to get the results for the typical person, so the mode, you have to do a two-step optimization on the quantile regression, and the symptotic theory will not be a normal distribution, so you have lots of problems in the inference. You can do it, but it's not easy. So there is a paper from Kato, if I'm not wrong, that do it. I think it was the first one doing it, to use quantile regression to approximate the mode regression. So these approaches, well, they tried several times. The one that is closely related to mine, it's the one from Lee, from 1989, that he tried to approximate the conditional density here using a kernel. The problem was he used a wrong kernel, just not a wrong, but he didn't choose it properly because he used a rectangular kernel. And the problem with that kernel is that it's not differentiable. So he was able to prove consistency, but he could not do any proofs for the asymptotics of the estimator. So he tried later with one that was already differentiable, the Epanishov kernel. And then he was also able to do the proofs, but basically he needed to do some assumptions that were not very good to use in some regression setting. For example, he needed some symmetry around the mode. And so basically the work stopped on this using this way until 2012, when Kemp and Santos Silva introduced their estimator. So basically the first difference is this one. So here, this is a bandwidth parameter. They assume it has a fixed one. Here they assume that it depends on the data. Let's just say it this way. And they use a general kernel, and they assume that this kernel needs to be, in this case actually, it needs to be 2 times differentiable. And so they prove, or they show in a special setting when we use a Gaussian kernel, basically we get out the linear regression with some weights. So those weights will disappear if the bandwidth goes to infinity. We get the mean regression. So basically what they are saying, if the data is well behaved, we would get out on that regression the same coefficient as the linear regression. If the bandwidth goes to 0, then we get the mode regression. The main drawback of this approach, it's a general drawback, at least that I'm aware, is that we have a slower rate of convergency. It's not a typical square root of n. Basically, you could approximate it for this case as b root of n to 7. Root 7 of n to power 2. This is basically because of the bandwidth that it goes a slower rate, so it basically has the power to make the approximation to the rate that it goes to the normal a little bit slower. So my first paper, I did the first expansion to final data. Well, because I worked mostly with final data, and because final data has a lot of flexibility, we could look at unities, we could do the time, we could do the defects through time, effects to the unities, effects, some multiplicative effects, some additive ones. We could some group effects also. I also tried to do some work on that. It's still unsuccessful. So I expanded this one for final data. First, I'm going to present just as a reminder the two fixed effects. So here we have effects on the unities, so the individual effect or the specific effect, and here we have the effects on time or through time, so the known as time effects. But here we expand also this one. Also expanded this approach. Instead of doing an additive one, we did a multiplicative one. And this is basically, I'm just going forward, because we can retrieve that case as a special one. So you are put some flexibility, some extra flexibility on the model at the cost of more difficult proofs, basically. So on this setting, we'll just forget this one. This is just saying that we are in a mode setting. We could forget about it. So basically, you have our FT. This is the unobserved common defects. We have their loadings. I could think about has their coefficients or the beta coefficients. You have the interactive component. Components a way of talking about this term. And we also have R, that is the number of time effects that we're going to put on our regression. So we already talked a little bit about this. So there are two ways of estimating something like this. We could do it in one go. For example, in a linear setting, there is a paper from Bay. There is a paper in 2024, 25 from Shen that presented, no, from 2024, it's not from Bay. It's not from Shen. So there's two ways of doing this. You could do the joint optimization. So we basically could try to retrieve all these parameters in one go, or we could try to do it by first finding the common factors, and then optimizing for beta and the loadings, and then obtaining the rest of the parameters. So this is easier computationally, mainly because instead of estimating like this number of parameters, the t-dimension disappears because we did it in the previous step. So this was actually my approach. I did a common correlated effects way. Just some small note to everybody. I put here Pazean. He came with the close formula a close way of doing it to the one I presented here. The only difference that he also put a dependent variable in the way to obtain the factors. We don't follow that way. We follow the way of a paper from econometric theory of Shen, I think it's from 2023. It is just easier also in the proofs and in the way of estimating the common factors. So how do we do it? So this is the multi-regression fully presented. So we have here, let's say the linear, we have here multiplicative part, but let's say the linear part. Here we are saying that we want to estimate the mode dependent on the beta parameters, the factors, and the holdings, and the joint objective function is this one. How I was saying, I want to first get this out and put here the estimated factors to get the estimation to be more easier to do. And also the proofs, because the syntactic, if you do the expansion, the Taylor series expansion, we will get dependencies on all three expansions, so the proofs get very harder. I think there are ways to do them. I tried some of them, I could not finish them all. So yeah. So before going to the next slide, the easier or the way that we propose to do it's the way from Shen. Basically, we average out to the units, and then we select the eigenvalues from these matrices that are higher than this value. Basically, also Shen has to do some simulations, and he proposed using this one. So we follow in the same footsteps. There are other ones that you could use. I saw that you could use two from Base, I'm not sure, from 2023, from his paper, because he would satisfy the necessary conditions. And say that let's say that you were able, using the way that you want to do it, you were able to found the common factors. And after you found them, we then replace here, and then you can treat the lambda parameters as a parameter to estimate jointly with the beta parameters. So this is basically the Kemp and Santos-Silva framework, just extended to final data and to common correlated effects. So we prove that our way to estimate the factor is consistent. It's basically the same one as previously presented, and some are simple conditions. The number of parameters could also be treated as known. Basically, I also put it here. It's just this condition, the simple condition, needs to be true, and if the condition is true, then we have this theorem is valid, and then you can treat the number of factors as known. After that, let's go to the optimization and retrieve the estimates. So we first prove the consistency for the beta parameters. We also prove the consistency for the holdings. You actually could treat the holdings just as a normal beta. This is the easiest way to do it in optimization. And since they vary to individuals, they could be also seen as an amplifying or reducing effect on the effects that the time has on the unit. I don't know if I'm making myself clear. We were also able to find the variance covariance matrix, and we also proved the asymptotic normality. Here we did this one differs a little bit from this one, because this we were able to do the proof when n and t goes simultaneously to infinity. Here we do the proof diagonally. That means the rate between r and t needs to be consistent, needs to be a constant. Say t divided by n or n divided by t needs to be equals to c. So n needs to be proportional to t. This is what also other authors have done, because it makes the proofs doable. In this case, I couldn't find a way to get out of the proofs. And the thing is, in this setting, is that our variance covariance matrix is a theoretical one. So we also need to later prove a way to get a consistent estimator. Basically, most simple, you just take out this distribution or this function and replace it with a kernel function, and you will be able to get a consistent estimator for the beta, for B and for G. And that would be how we would get the variance covariance matrix for beta parameters. We didn't do the proofs or the loadings manually, because most people are only interested in the inference on the beta parameters, but basically the proofs will be kind of the same as we did for B. You only need to do some replace on the syntactical expansion. You will get around the same result. Um,
It's
more
4 minutes, Joao.
Sorry. So we see that we also have the same rate, that estimator vanish goes to infinity or goes to normal distribution. And here we get the convergence rate of the estimator. If we put here a 2, that is the same parameter of Kemp, we would get the same as 2/7, that is the rate found on Kemp and Santos-Silva. In doing the work, I needed to assume that we have a high order kernel. And I think it was order 11, so the kernel needed to be 11 times differentiable. Instead of doing that, I just use a high order kernel that's always differentiable. And then we replace on the function that we want to optimize for that function there, and we will be able to obtain the estimates. We also put some things about optimization. We need to get, or it's good to have good initial guesses for the parameters, and use the generated similar to the annealing, generalized similar to the annealing, because the area could be a little bit flat because of the bandwidth. So use some stochastic method, or do a 2 steps like use a Newton and then some stochastic method, so that we do not end up in a local minima. Yeah, because I just changed the sign of a minimization problem. So then we need to also estimate the bandwidth. This is our proposal. It's the same as in Kemp. Here this is a small change. And we did also some small simulation process. Basically, we put some skewness and some heteroscedasticity in our data, and we check if beta equals 1, beta 1 equals 1. We found some small biases. Basically, those biases will disappear with n and t when n or t or both grow. And the case if you have to choose the bandwidth here, my recommendation is to use the 1.2, because it has better results than the 0.6. Even in other simulations that I also did, this one could keep being the best one somehow. So basically, it's the work that we did. We could expand this for weakly dependent cases, for autocorrelated factors, for non-stationary factors. We could do usual. I'm thinking about a mildly explosive case. There could be some expansion be there, and basically it's that they have that it's that I could do after this work. So my presentation is over. Thank you, everybody. Now, if you want to do some questions.